Hi, I'm here to talk about Pane, which is a system for programming with visible data. The kind of programming I'm interested in here is data processing. And when I say data processing, I mean it in the broadest possible sense. Data processing is turning one piece of data into another. This includes scientists analyzing lab results, or geographers making maps, artists crafting iambic pentameter Twitter bots, even people programming e-commerce servers. All of these people are processing data. Functional programmers have a special relationship with data processing. To a functional programmer, all programming is data processing. Functional programming is built out of pure functions, those that take in data and produce new values without side effects. A benefit of this way of thinking is that pure functions can be composed together in an especially comprehensible way to build up big programs from small ones. The execution of a compound function can then be seen as a chain of distinct concrete values connected to one another by smaller functions. In the live programming community, we want to give people the ability to see what they're doing when they program. And it seems that functional programming offers a fantastic opportunity to do this. You can visualize functional programs. All you need to do is show the data that's sitting there at every step. Since your program is not much more than the values being transformed, seeing the values at every stage gives you a powerful window into what your program is doing. But the reality is that functional programmers don't tend to program this way. They tend to program using representations that look a lot more like this. And the tooling that functional programmers are most used to using isn't tooling based around data visibility, it's static typing, which provides an indirect window into what a program is doing in lieu of direct live visibility. But I believe that those scientists and artists and data wranglers in general deserve to see the data that they're processing. So we'll try adopting a principle, which I call the principle of radical visibility, which says that all data should be visible by default. The project that I'm going to show is in many ways just a straightforward exploration of the consequences of this principle. The project is called Pane. It's a prototype live programming interface built for general data processing. It's built on a functional paradigm, and you'll see that design-wise, it occupies a pragmatic niche between text and visual flow-based languages. And all along, the intent is that the system follow this principle of radical visibility. So I'm going to spend about 10 minutes sharing a demo with you. I'll show you the mechanics of how Pane works, and we'll see some of the things you can do with it. Afterwards, we'll zoom back out and reflect on some general patterns. Okay, so here's Pane. A document in Pane is made up of a set of function definitions. Here there's a function called normalize, which normalizes a vector. On the left are the inputs to the function, in this case, a single input called v. And on the right is the body of the function's definition. Already we see something a little bit unusual, which is that the programmer who made this function provided a value, an example value for the input v. This is a necessity to follow the principle of radical visibility. If we don't have values for our function, we can't see the values flowing through our function. So if we click on the input v, we see a list of other values that the programmer has provided as examples. If we click on these, we'll see what those values do when they flow through the function, including one value that creates some interesting results. We can also edit one of these inputs with the keyboard to try out different values, or we can grab the numbers and scrub them around to get a more direct, continuous feel for how they affect the program. So that's how the inputs work. Let's look now at the right-hand side. For this function, its definition consists just of one connected graph of nodes and connectors, although we'll see that this isn't always the case. These nodes contain values, such as the input value, and in this case, these calls, these arrows represent calls to other functions that have been defined in this document. So for instance, here's a length function, which I've hidden right now just to keep things simple, but I could show that by clicking this and you'll see this function here. Or even better is that I could press this plus here to see that definition in the specific context of the values that are being input to the call. So here, if I change this, we'll see how this length function works in the specific context of its input. So this call that's being used in the length function is different from this length and divide call because this call is just running raw JavaScript code. Pane is built off of JavaScript, and at the bottom, everything's just running little snippets of JavaScript, which gives it a lot of flexibility. So one other important thing to mention is that although nodes can be connected by these call arrows, they can also be connected using names. We already see that in this function because these two nodes make a reference to V using its name rather than any direct connector. But we can also use names to connect intermediate values. So to show this, I'll take this value here, which is the output of the length call, and I will drag it out to here. So now the length is being computed in this top graph. And then to hook that up here, down here, we will give this a name, like we'll call it how long, and then we'll refer to that here. So now we have essentially the same function we had before, but factored into two calls instead of one single graph of calls. Pane gives the programmer the flexibility to structure their function either way, depending on what's best for their function. So now that we've seen the basic structure of how these graphs work, I'll show you how to build something from scratch in Pane. So as an example, we'll make a function that greets a list of friends. So I have here an example list of friends, and I'm going to make a new function called greetFriends, and it's going to take in one input, which is that list of friends. And I'll put in this data as the example data. So to greet our list of friends, we're going to generate a string which says hello to them, and it's going to use their full names because we're very proper. In order to extract out the full names, we want to do something to each element of this array. When you want to do something to every element of an array in a functional context, you do a map operation. So I'll right-click on this and say Run Map. So we're starting to build the body of this function, and the one call that we're making is to map. Underneath the map arrow is the body of the map, or you could say the per item function. This is a function that's going to run on every item of the list. Now, just like everywhere else in Pane, you need concrete examples for everything you do. So this per item function is given as an example input an element of this array, and it's an element that you can pick. If you hover over these different elements, it switches which example it uses, so you can make sure that it works in the context of every item. By default, this function is just returning back the item that it was given, so it's the identity function, so nothing interesting is happening. But once we do something interesting to this node, we'll actually see an interesting output for the map call. So let's get people's full names. The full name is a function of the first and the last name combined in a certain way, so we want to extract that information. Pane has a feature called extract field that we can use for this. We put the mouse over the first name and we say extract first. Then we put the mouse over the last name and we say extract last. Now we have two separate calls to extract out the first and the last names. They're a little verbose though. They take up a lot of space, but we can collapse them, which changes them into these nodes that have inline code underneath them, which for simple calls like this is often easier to read. Now we want to combine these two values, so we'll drag the second one into a call together with the first one. By default, it just puts them in a list, but we'll change the code for this to instead combine them with a space and make a full name. So now when we look at the output to this map, we're successfully creating these two full names. Now all we need to do is combine them together with some other text to make a sentence, and that's just some standard JavaScript code. So I'll drag down a reference to this node here, which it alerts me is nameless, so I'll call it full names. And now that we have the full names down here, we'll run some code to join them together with the text and say hello. Great. So now that we've seen this small example of processing data with Pane, I'll show you a much larger example. This example has to do with following a chain of free association from word to word. So specifically, it's using an API at bighugelabs.com to find the synonyms of a word. So this function called synonyms takes a word, puts it into the URL to make an API call, and then it gets back this result, which is a JSON result shown as nested boxes. And you can see that this result is a little complex because the API returns data for each different part of speech that this might be. So if we just want to know the synonyms, disregarding which specific part of speech it is, we want to map through each different part of speech and just extract out the synonyms. So that's what this map does. It loops through each different part of this object and extracts out .syn. So now we have just the synonyms on the top level, and we can use this other function I've defined called join lists to merge them all together into a single list. So now that we have the list of synonyms, we can choose one at random, which is what this function random synonym does. It takes a word, uses that function up above to find its synonyms, and then it chooses one at random using a random choice function that I defined. So a random synonym of fun is merriment. So down here in this scratch space, I've started with the word and I've fed it through the random synonym function several times to see where it goes. So I guess live can become hold up, can become go, can become whirl, can become twiddle. Sort of funny. As another example, I'll try code. To code is to inscribe, is to cipher, is nothing, is zero. This API combined with a little bit of code is enough to create these interesting, artistically provocative processes. So the last example that I have to show has to do with something that's very deep to what Pane is all about, which is visualization. So I have here a function called add vectors, which adds two vectors together. And it has the nice properties that Pane gives you of liveness and visibility to all values at every stage, but it's not really showing these values in the way that they ought to be shown, because these are vectors, and we all know a really powerful way to see vectors as a little arrow. Presumably, seeing these values as vectors would offer a lot more insight than just seeing a bunch of numbers. To remedy this, I've added a feature to Pane to let programmers create graphics using functions and then to use those graphics to make pervasive value visualizations. As an example of what I mean by creating graphics with Pane, I'll show you this function called makePath, which takes a list of points with XY coordinates and joins them together into a path. And this is just a standard reactive program like anything in Pane, but it's creating graphics instead of data. As another example, here's a function called combine diagrams, which takes an array of these diagram objects and puts them together. So using these basic functions, you can create larger diagrams, and hopefully you can actually see what a vector looks like. So here's a function called drawVector. It takes in a single input, which is a vector, and then it makes the different pieces of the arrow that we want to use to draw it. It makes a line for a shaft of the arrow. Then it makes a colored arrowhead in a standard template position, followed by rotating it and translating it into the right spot. Once you put these pieces together, you get the arrow that we want. If I mess around with the arrow's coordinates, the vector's coordinates, we can see the arrow react as we'd expect. So that's a great sign. So we have a function that makes an arrow, but now we want it to be used anywhere that we have a vector. So here's a function called visualize vectors, which takes in an input and checks to see that it looks like a vector using a conditional structure for Pane that I haven't shown yet, but it's what you'd expect. But if the input looks like a vector, then you put it into drawVector, draw it like a vector. Otherwise, you don't return anything. So this is just a filtered version of this function that only runs on vectors. So we can set this as a visualizer. We right-click on this and say Enable Visualization. Once we do this, every single value that's being shown in Pane is run through this function to see whether it ought to be used to visualize it. And in this case, all of these values are. So if we take one of these values and change it, we see all of its representations of all the vectors shown the way that they ought to be shown as actual graphical vectors. So the vision for programming in Pane involves programmers creating visualizations like this as they program to be able to see the data that's relevant to them in a rich way.
I have one more example of the fun that you can have with graphics and visualization in Pane. It's this function I made called triple. What triple does is it takes an input diagram, it scales it down by a factor of 2, and then it pushes it in 3 different directions. It pushes it down, it pushes it to the top right, and it pushes it to the top left. Then it combines these 3 different versions together to create this tripled version of the original shape. So what we'll do is we'll start with a big polygon, and we'll triple it. Then we'll triple that again. And triple that again. You can start to see what's forming here is this fractal triangle. But it's not just a fixed image, it's the output of this program. So we can change the different parameters, like try using smaller pentagons to make it. Or we can change the number of sides. Maybe try 6 sides. So now the shapes are fitting in a kind of neat way. If we make them larger, they start overlapping in a lot of really neat patterns. I think this shows some of the potential of being able to see the intermediate values in a program. If we had just made a program to make this triangle, we only would have created a single final output. We wouldn't have thought to explore the different stages of the program this way. So my hope is that systems like Pane, by providing deep visibility, can provide for a lot more creativity and exploration.
So now we've seen how Pane works, and I want to take a step back and look at some of the design decisions that guided its development through the lens of comparison. One comparison jumps out immediately. Pane looks a lot like a patch-based programming environment. I'm referring to systems like MaxMSP, or Grasshopper, or LabVIEW. These all share a lot of commonalities with Pane. They all have lots of little boxes hooked up with little wires, just like Pane. But there are two very important differences that distinguish Pane from these environments, which I will call patch-based programming environments. The first difference has to do with what might at first seem like a subtle point. In patch-based environments, the boxes represent functions, or processes. This means that data is represented by the lines connecting the boxes. You can schematically represent that like this. You've got data traveling along wires, and you've got functions living in boxes. And that's actually the opposite of what happens in Pane. In Pane, the data are what make up the boxes, and the functions producing new data from old data are represented as wires. And this is an important distinction because it reflects fundamentally different metaphors that these systems are using. Patch-based systems were inspired by electrical networks, like modular synthesizers. With a modular synthesizer, you have modules that do different things, little function boxes. You patch them together with cables, and then signals travel from one box to another along those cables. But that means the data, the thing you're most interested in seeing, is trapped and invisible. It's inside the wires. When you use a modular synthesizer, you don't have visibility by default. If you want to know what's happening on one of those wires, you need to patch into it and hook up an oscilloscope. It's a peeking through a keyhole kind of visibility. These patch-based systems follow the electrical metaphor, so they're bound by the consequences. If you want to see the data on their wires, you need to plug in special nodes, virtual oscilloscopes. But by flipping the role of nodes and connectors, Pane foregrounds the data and explores a different metaphor. Pane is closer to IKEA assembly instructions, or this wonderful cookbook by Katie Shelley, which shows flowcharts of recipes. Like these, Pane shows snapshots of a process, rather than disembodied instructions. So Pane foregrounds the data. When you foreground the data, you get the room you need to see the data. You also get handles for acting directly on the data. Pane has begun to explore this with the extract fields operation, and there's a lot more to push on in that direction. One other difference between Pane and patch-based environments has to do with layout and structure. Here, again, the difference comes down to the underlying metaphors that these systems are based on. There's a common criticism of patch-based systems, which is that programs can quickly become monstrous spaghetti. I think this is a result of these systems' single-minded commitment to the patching metaphor, that all a program is a web of boxes connected with cables. Pane doesn't follow that approach. It uses graphical elements only at a small scale to show small chains of connections. But at larger scales, Pane opts instead for a literate document-based metaphor that's closer to traditional programming. For instance, Pane makes it natural to connect a program together using names rather than physical connectors. Humans are pretty good at naming things and referring to them by names, so that's what Pane lets humans do. Pane deviates from the patch-based orthodoxy in a few other ways. It allows for the use of small snippets of code for situations where expressing the snippet as a network of nodes would be unenlightening. And Pane uses nested blocks for list operations and conditionals, showing structures of containment instead of dangling nodes. Altogether, this pragmatic hybridism makes Pane look a lot less noodly while still revealing structures and connections. I claim that this hybrid graph plus document metaphor gives a greater legibility to Pane code. Also, by following traditional hierarchical programming techniques, this provides what an environment needs to scale from small and simple to complex. Nodes and wires alone provide a poor foundation for this. Pane is based around these two key design decisions, chosen in the process of following the principle of radical visibility. These decisions have positioned Pane at an underexplored point in the live programming design space, and I hope that this work inspires further ventures into that territory. Last, I'd like to tell you about a few directions this work points in. I'm interested in three directions in which to take this work. One is to do a better job of showing data. Another is to do a better job of working with data. and a third is to do a better job of connecting with the world. There are many examples for each of these categories. I'll just mention one example for each. One way that Pane could show data better is through relational visualizations. Here's a translation function in use in present-day Pane. It's nice that we can see these shapes and see the vector that relates them, but it takes special mental gymnastics to put these images together and see how the vector relates the centers of the polygons. That's because each visualization here lives in its own little world, its own little box. Often, visualizations are most powerful when they combine different things into the same space. So Pane should let us do that, as this mockup demonstrates. And the power of visualizations that relate multiple values goes well beyond, obviously, spatial cases. Superimposing time series charts is another clear example. That's one way Pane could do a better job of showing data. Pane could also provide more ways for programmers to work with data. That means using direct contact with data as part of the process of building programs. Here's one idea. Suppose I have this array of arrays, and I want to join all the arrays together. Maybe I don't know what the right function for this is. So I add a question mark call, and I fill in what the output of the call should be. I'm asking Pane to use this example to search for a function. And Pane finds just the right function and slots it in. This is programming by example. It's an idea plenty of people have done deep research into, but I'm particularly excited by how well it seems to fit with Pane's example-centric style. The last line of future work is about fitting Pane into a broader context and making it an effective tool in the real world. Here's an example of what I mean by that. It's fun to make visualizations in Pane, but it's really not the right tool for the job. Apparatus, on the other hand, is a direct manipulation editor where you drag shapes around and program them directly. Apparatus is designed around the medium of diagrams, so it's a much better environment for making visualizations than Pane is. I think you should be able to make visualizations for Pane in Apparatus. Or, if you're making an explanatory interactive diagram in Apparatus and want to do some kind of data processing that goes beyond what Apparatus is good at, you should be able to pull in a program that you made in Pane. In general, this points towards a vision of a vibrant ecosystem of heterogeneous domain-specific live programming tools that can each leverage each other's strengths. With that, I'd like to extend thanks to all the people who have contributed to the projects that inform this work, and to the live reviewers and the whole community.